In this lesson, we are going to take a look at the relationship between the derivative of a function and the derivative of its inverse. There is a relationship between the two, and once we find that relationship, we can use that relationship to find the derivatives of inverses without using the limit definition. Also, what we're going to do is we are going to use that relationship to actually derive some of the inverse trig function derivatives. So to get started here, you can see in pink, I have a function labeled as f. It's just some generic function f. And on that function, I have another generic point labeled as AB. So my x-coordinate is A and my y-coordinate is B. Now, when you have an inverse function, that inverse function is formed by switching all the x and y coordinates of f. So f inverse is going to be all the x and y coordinates swapped. So if you have the point AB on f, on the inverse, you're going to have the point BA. Now, recall what the derivative is, and I'm going to call the inverse of f, I'm going to call it g. So f inverse, I'm going to call it g. Now recall what the derivative is. The derivative is the slope of the tangent line at any point. So if I wanted to find the slope of the tangent line of f through that point x equals a, what I would do is I would take the derivative and evaluate it at a. And the same thing goes for g. If I wanted to find the tangent line on G that passes through the point x equals b, I would find the derivative of g and plug in x equals b. Now, if I imagine that I draw my tangent line, let me see if I can draw it in a different color. Let's use purple. I'm going to try to draw it so that it touches only one point. We'll call that line 2. And the tangent line that passes through AB on F, we'll call that line 1. Now you can see that when you have those two tangent lines, what happens is they intersect at the line y equals x, which means this point where it intersects has the same x and y coordinate. So let's call this point C, C. And it has the same x and y coordinate because it's on the line y equals x. So the values of x and y should be the same. So if I wanted to find the slope of the tangent line L1, the slope of a line is just the change in y over the change in x. And I have 2 points on L1. I have the coordinate AB, and I also have the coordinate CC. So I'm going to take the change in x over the change in y using these 2 points. So let me highlight those 2 points. So we have this point and this point. That's what we're using to find the slope. So I take the change in my y's, which is b minus c, and I'm going to divide by the change in my x's, which is a minus c. Now, if I do the same thing for the inverse on the green function, function g, if I wanted to find the tangent line that passes through that point x equals b, but it also passes through the point CC, so I'm going to use those 2 points. Let me highlight them in a different color. I'll use yellow. So I'm going to use the yellow points to find the slope of g. So I'm going to take the difference in my y's, which would be a minus c, over the difference in my x's, which would be b minus c. Now, if you notice, the slope of tangent line 1 is the reciprocal of tangent line 2. These are reciprocals. So there is our relationship. Now, if I wanted to write this in a generic way and not in just a way for one specific point AB, I would write it like this. I would have that the derivative of the inverse, which we call g of x, is equal to the reciprocal of the derivative of f evaluated at g of x. So this way here is written with the inverse notation, and then this formula here is written with the inverse notation just written as g. So g is the inverse. Okay, now we're going to apply the inverse function theorem in this example. And the function that we're using is g of x is equal to x plus 2 over x. So if you recall, the inverse function theorem says if you're trying to take the derivative of g of x, and you know the inverse function, you can find the derivative of g of x by taking 1 over the derivative of the inverse, which is your f, and then evaluate it at g of x. So the first thing we need to do is find the inverse of g of x. So g of x is x plus 2 over x. Now, if you recall from college algebra, to find the inverse, you need to swap your x's and your y's and then resolve the equation for y. So when I swap my x's and my y's, I'm going to get x is equal to y plus 2 over y. Now, I'll let you do the algebra on this, but when you resolve this for y, you're going to get that y is equal to 2 over x minus 1. And that's your inverse of g, which the theorem calls f of x. So now I have to take the derivative of f of x. We can use the quotient rule, and when we do that, we get the derivative is negative 2 over x minus 2 squared. Now, once we get the derivative of the inverse, we take the reciprocal of the inverse and then evaluate it at g of x. So I'm going to flip the derivative upside down. So I have x minus 2 squared over negative 2. That's the reciprocal of the derivative of f. And then when I plug in g of x, everywhere I see x, I'm going to replace it with x plus 2 over x. So I've got x plus 2 over x minus 2 squared all over negative 2. I'm going to finish down here. When I clean that up and I simplify that, I'm going to get negative 2 over x squared. So that's a fairly lengthy way to do it, rather than just finding the derivative using the quotient rule directly. If we found the derivative of g of x using the quotient rule directly, we would still get the same answer, and you can verify that. But the reason why we're using this and getting comfortable with this theorem is, like I said, once we familiarize ourselves with this, we're going to use this theorem in order to derive the inverse trig function derivatives. Okay, the next example, same thing. We have g of x is equal to the cubed root of x. So the inverse of this is going to be f of x, and when we take the inverse of the cubed root of x, we are going to get x to the third. So these are the inverses. Now the theorem says that the derivative of g of x is 1 over the derivative of f of x evaluated at g of x. So I have to find the derivative of f of x, plug in g of x, and then take the reciprocal. So the derivative of f of x is 3x squared. Now when I plug in g of x, I get 3, and then in parentheses I replace it with the cubed root of x, and then squared, which is the same thing as saying 3 times x to the 2/3. So now I have the derivative of f evaluated at g of x, and the last step, right, is to take the reciprocal. So 1 over f prime of g of x is 1 over 3x to the 2/3, which we can write as 1/3 x to the negative 2/3 if we want. Either way, these are the same thing. This example says find the equation of the line tangent to the graph of y equals x to the 2/3 at x equals 8. So the first thing that we need to do is find the derivative and evaluate it at x equals 8. So I'm going to find the derivative of y with respect to x. So I have x to the 2/3, so I want to bring the 2/3 down in front and then decrease the exponent by 1, which would give me negative 1/3. And then I want to evaluate this at x equals 8. So when I plug in 8, I'm going to get 1/3. So this is the slope of the tangent line at x equals 8. So now what we need to do is plug in a point so that we can find b. I want to use x as 8 because that's the point on the tangent line. So I need to find the corresponding value of y. So if I plug 8 back into my function, 8 to the 2/3, I am going to get a corresponding y value of 4. So I'm going to use this as my x, this is my y, and my slope is 1/3. So I have 4 is equal to 1/3 x, which is 8, plus b. When I solve this for b, I'm going to get 4/3. So my equation of the tangent line is y equals 1/3 x plus 4/3. So this is an example of applying the power rule to a fractional exponent, which all the rule still stays the same where you want to decrease it by 1, but we haven't practiced one like that yet where we have a... Okay, so now we are going to actually derive the derivative of inverse sine x by using our inverse derivative theorem. So recall that if I want to find the derivative of g of x, I'm going to take the reciprocal of the derivative of the inverse and then evaluate it at g of x. So f of x is the inverse of g of x. We know that the inverse of inverse sine x is just sine x. Inverse sine x and sine x are inverses. Now if I take the derivative of sine x, I get cosine x. Now if I evaluate the derivative of sine x at g of x, that gives me cosine of inverse sine x. So now this is what we have. I have the derivative of g of x, which is the derivative of inverse sine. Now I take 1 over the derivative of the inverse evaluated at g of x. So that's what we have right here. So I'm going to fill that in. Cosine of sine inverse x. Now, if we look at our triangle, if we think back to trig class, remember inverse trig functions, the output would be an angle, right? If we have our regular trig function, we plug in the angle, we get out a ratio. When we invert that, that means we plug in the ratio, we get out the angle. So that inverse sine x represents some angle. If I have sine inverse x is equal to theta, then I can also write it like this. Sine theta is equal to x. And remember, sine is opposite over hypotenuse. So the opposite side of the angle would be x. The hypotenuse would be 1. And just by using Pythagorean theorem, I would find that this other leg would be 1 minus x squared. So now if I take the cosine of this angle, I'm going to replace sine inverse with the angle. That's this angle here. And if I find what the cosine of that angle is, the cosine is adjacent over hypotenuse. So I end up getting in the denominator the square root of 1 minus x squared. So the derivative of inverse sine x is 1 over the square root of 1 minus x. Now if I use that same style proof and I apply the inverse function theorem for the other inverse trig functions, what I would have is that the inverse cosine function has a derivative that's negative 1 over the square root of 1 minus x squared. I would find that the inverse tangent function has the derivative of 1 over 1 plus x squared. I would find that the inverse cotangent function has the derivative negative 1 over 1 plus x squared. I would find that the inverse secant function has a derivative of 1 over the absolute value of x times the square root of x squared minus 1. The cosecant inverse function would have the derivative negative 1 over the absolute value of x times x squared minus 1. And then, of course, we can also write down the inverse sine, which we found, which was 1 over the square root of 1 minus x squared. Okay, so now let's practice. So this example says we're going to apply the chain rule to the inverse sine function. So it says apply the chain rule to find the derivative of the inverse sine function of g of x and use the result to find the derivative of h of x, which is inverse sine of 2x to the third. So if I am finding the derivative of h of x, which is inverse sine of g of x, using that we found that the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. But what we have to recognize is this is an x. Whatever's in here, we have to plug in for x. It's a substitution. So if I just had the inverse sine of x, the derivative would be 1 over the square root of 1 minus x squared. So whatever is inside the parentheses has to be squared down here. So now I'm going to replace this with g of x squared. And then because g of x is an inner function, using the chain rule, we have to multiply by the derivative of g of x. So now when we apply this to the actual function that they give us that has g of x plugged in as 2x to the third, h prime of x is going to be 1 over the square root of 1 minus, and whatever is inside here gets replaced for x. So I'm going to put in parentheses 2x to the third squared. Don't forget that all of that is going in parentheses. This whole thing is replacing the x. And now we have to multiply it by the derivative of the inner function, which is 2x to the third. So when I multiply that by the derivative of 2x to the third, I get 6x squared. Now when I clean this up, and I take 1 over the square root of 1 minus 2x to the third squared times 6x squared. On the top, I'm going to have 6x squared. On the bottom, I'm going to have the square root of 1 minus, and then I have to square the 2x to the third. So that's going to give me 4x to the sixth. In this next example, we're going to find the derivative of inverse tangent of x squared. Since we have that inner function in there of x squared, we have to remember to use the chain rule with the formula for inverse tangent derivative. Okay, so the formula for inverse tangent derivative is 1 over 1 plus x squared. So whatever you're taking the inverse tangent of, you have to square it here in our formula. So the derivative with respect to x of tangent inverse x squared is going to be 1 over 1 plus, and then in parentheses is my inner function, which is x squared, and then I have to square it. So this is what I'm subbing in here. And then by the chain rule, I have to multiply it by the derivative of the inner function, which is 2x. And when I clean that up, I get 2x over 1 plus x to the fourth. So this is my final answer of the derivative of inverse tangent x squared. The next example, we're going to use the product rule with an inverse trig function. So I have two functions multiplied together to form h of x. So I'm going to call f of x x squared, and then g of x is going to be inverse sine x. So the derivative of f is 2x, and the derivative of g, using our formula for the derivative of inverse sine, I get 1 over the square root of 1 minus x squared. So now, using the product rule to find the derivative of h of x, I have the derivative of f times g plus the derivative of g times f. So f prime is 2x, and g is inverse sine, plus the derivative of g, which is 1 over the square root of 1 minus x squared, times f of x, which is x squared. Now, there really isn't a whole lot that we can do to simplify that, so I'm just going to leave it alone. There isn't really any like terms or anything like that that we can combine. In this last example, we are going to find the velocity using the inverse tangent function. So the position of a particle at time t is given by the position function inverse tangent of 1 over t for time greater than or equal to a half. Find the velocity of the particle at time 1. So in order to find the velocity, we need to take the derivative of the position function. And so I need to take the derivative of inverse tangent 1 over t, and we know that our derivative for inverse tangent is 1 over 1 plus, and then inside here, that would be our inner function. So our inner function here is 1 over t, so I'm going to plug in 1 over t here. And then I have to multiply it by the derivative of our inner function using the chain rule. And so we have to take the derivative of 1 over t. You could either use the power rule or you can use the quotient rule, but either way, when you take the derivative of 1 over t, you're going to get negative 1 over t squared. So now when I clean this up, I'm going to take across the top, I'm going to take 1 times negative 1. That gives me a negative 1. And then if I take t squared and distribute that in the denominator of the first fraction, I'm going to get t squared plus 1. So here is my velocity function. Now if I want to evaluate it at t equals 1, I plug in 1 for t. So that will give me negative 1/2. So I know that since the velocity is negative, that it's going in the opposite direction in which it has started. And so our final answer is v of 1 is equal to negative 1/2.